Okay, so it's a great pleasure to have Atabey Kaygun from Istanbul Technical University. Today, we are going to hear about filtered complexes, Matroids, and Cobordisms.
Thank you for the invitation. So this is a joint work with my PhD student, Ismail Güzel. Essentially working with him on these topological data analysis stuff. And these things that I'm going to talk about today came in one paper that we're trying to write at the moment. So this is ongoing research, and some of these things are not going to be fully fleshed out because we're still working on it. But there are some interesting questions, and there are some deep theory underneath, topological theory underneath. So I would like to talk about these things today. So let me start with the concrete problem, this is a very old problem actually, but I'm going to talk about the relationships between this newly concocted area of topological data analysis as well. So here is the thing, we have a finite sample of points from a topological space M, and we don't know anything about M, we just have the finite sample of points. And the questions we would like to answer today are there are two questions. One, when does D capture the topology of M in whatever question you have in your mind? And the second thing, of course, is that how do we calculate topological invariance of M using only D? Okay, so what we are trying to do, essentially, we are trying to take a continuous object, a topological object, M, and try to understand it using a finite sample of points, a finite approximation. If you know a little bit of the history of topology, you actually should notice that this was the original intent of topology. These people were trying to break it down into a finite set or a finite collection of points or a finite gadget from a continuous object and try to break it down to these finite pieces. The specific result I'm going to use today heavily is Borsuk Ulam's nerve theorem. So we start with a topological space and an open cover. And then, but we want the open cover to satisfy the following property. Take any subset of these open sets and take the intersection. If the intersection is contractible for every subset, then there is this thing called Czech complex, or the nerve of this covering. And then this covering, the nerve of the covering is homotopy equivalent to X. So what happens is that essentially you transfer the problem of topology of X to this combinatorial information about the intersections of these open covers, provided that they satisfy topological property that the intersection is contractible. So we answer the first question in a sense. If I can, well, let me go on. Okay, so this is going to be the main tool that I'll be using today quite heavily. Now, in practice, we don't work with arbitrary manifolds. We usually work with embedded affine manifolds in Rn. In practical terms, the data that applied mathematicians work are data in terms, well, given as vectors and elements in Rn for some set, for some number n. And here they use the term, the number of features, and the coefficient, I mean, the components are going to be just real numbers. And the metric that we use either comes from the metric or Rn or induced geodesic distance on Rn. Okay. Most of the time, people in applications don't even go to the geodesic distance. They use the inherent or the underlying metric in Rn, Euclidean metric, L1 metric, LP metric, the max, whatever you have. Okay. So today, I'm not going to specify anything about the metric. You can, for all practical purposes, I'm using the Euclidean metric on Rn. So we have some sort of a question, some sort of an answer for question number one. How do we capture the topology of M by using a finite set? in our case, since we are talking about the finite collection of points embedded in Rn, we want this set to be some sort of dense in the manifold that we don't know, okay? Which means the union of the open balls centered at these points should actually cover the whole space M. So this is what I would call epsilon dense. In that case, using Borsuk's result, that if this thing is epsilon dense, and we know that the balls are contractible in Rn, or any intersection of balls are contractible in Rn, this collection of open balls, or anything combinatorial that this check complex or these complexes that I get out of these collection of balls in Rn, capture the topology of M. So that's the answer for question number 1. Relative to a specific choice of epsilon, of course. The second question is that if I have this collection of balls, if I have this collection of points in Rn, how do I calculate the topological invariance of M using this only finite set of points? This answer is actually predates Borsuk-Ulam's nerve theorem much, much earlier, because originally when people were doing topology, they were using CW complexes or these simplicial complexes, which essentially does the following steps. You take the manifold, you triangulate the manifold, from the triangulation, you construct a simplicial complex, and then you calculate homology or homotopy. So this idea that take a continuous object, approximate with a finite gadget, and then calculate the topological invariance of this complicated continuous object using a finite sample of points is at the heart of topology anyway. So this is what has been done since the past anyway. So the second question is actually this generating question of topology. But I mean, there is no single way of calculating the homology or homotopy from a finite gadget. So what are we going to do today? I'm going to look at two specific simplicial complexes. One of them is the check complex, and the other one is the Rips-Vietoris complex. So let's say I have n+1 points. I will write them as a0 up to an. In my, these are just n+1 points from this finite collection D. And I want to construct a simplicial complex. So I would like to construct an n simplex out of this n+1 points. So I will do in two different ways. In the check complex case, this n+1 point forms an n simplex if and only if the full intersection of all of these balls is non-empty. So I will take an epsilon ball around each of these points. I will intersect all of these balls. If the full intersection is non-empty, this n+1 points form an n simplex. In the Rips-Vietoris complex, I'll do something different. Instead of asking all of the intersections being non-empty, I would only ask if the pairwise intersections are non-empty with epsilon divided by 2. So in other words, saying that the pairwise points have distance less than epsilon. Okay. Of course, the thing is, check complex is computationally difficult. Why? I would have to make sure that all of the points, all of these balls intersect. In the Rips-Vietoris complex, all I have to do is just take these pairwise intersections or pairwise comparisons. So the computational complex, if you will, of the first one is 2 to the n+1 because I will have to do intersections for all subsets. For the second one, I will have to do only pairs. Which means, computationally speaking, check complex is a lot more expensive than the Rips-Vietoris complex. However, they capture the same topological information. You can these two things are, filtration-wise, they are actually equivalent. So here's an example. Let's say I have a finite collection of points sampled from the annulus in R2. Okay, the leftmost is small epsilon, middle one is kind of like a choice of a middle size and epsilon, and then the last one is a larger epsilon. Now you see that the choice of the epsilon changes the structure of the simplicial complex, either variation. You can use the check variation, you can use the Rips variation, doesn't matter. You see that there is no universal choice of an epsilon. This choice of the epsilon, which constructs this collection of balls, and from the collection of balls we construct the simplicial complex. The choice of the epsilon is heuristic. It depends on the sample of points. The second question is, how do we choose this epsilon? Since there is no universal epsilon, there should be some sort of way of, maybe there is a good way of deciding which epsilon I'm going to choose. Since this depends on the epsilon, I should be able to make this computation with respect to epsilon. There's going to be some sort of filtration. Now, you see from here, there's a big problem. If epsilon is small, then D is not epsilon dense. I'm not getting anything topological about the, or I'm not getting the right topological invariance. If epsilon is too large, then the check or the complex is going to be contractible. Look at the example here. The leftmost complex is just a bunch of collection of points. So there is no first homology, there is no second homology, there is nothing there. It's just a zeroth homology, and zeroth homology essentially encodes the number of connected components. You get this finite number of connected components. Well, technically, since let's assume that this is sampled from the annulus, I should have one connected component. So H0 has to be one dimensional. There should be a circle inside, so H1 has to be non-zero and one dimensional, and H2 and higher should be zero. All right. So the first one doesn't capture the right topology. The last one doesn't capture the topology either. The first one is too small, and the second one is too large, or the third one is too large. So I need something in the middle. Okay. Which means I will have to work with filtered complexes, because for each epsilon I have a simplicial complex. And if I change this epsilon, I will change the simplicial complex. And when I change the simplicial complex, I will change the homology or homotopy, whatever topological invariant you're calculating. Okay. So since the parameter epsilon is in the real numbers, this is a linearly ordered set. So it's a well-ordered, linearly ordered set. I shouldn't say well-ordered. Although it is. No, it is not well-ordered. Anyway, it's not the big deal. So it's a linearly ordered set. And what happens is that since this is a filtered object, if my parameter epsilon is less than my parameter eta, there is going to be a map of complexes. Actually, this map is an injection, because what happens is that if you increase the filtration parameter, your complex actually increases, or the size of the complex actually becomes bigger. Let me go back to this picture again. What happens here is that once you start enlarging these disks around these points, these disks would start intersecting. And if you remember the definition of the Rips complex, if 2 points are within epsilon neighborhoods of each other, then I will put a one simplex in between them, which means if these balls touch at epsilon divided by 2, then I would put a line in between them, or one simplex in between them. If I have a collection of 3 points and all of these points pairwise are epsilon distances of each other, I will put a triangle, a full triangle in between these 3 points. All right, which means these complexes grow as epsilon, this parameter is increasing. So this is kind of like as I said, it's a filtered complex. Okay, so this map here is not an arbitrary map, it's just an inclusion map. Now, that means since I have these inclusions of complexes as epsilon or the parameter grows, I will have induced maps in homology. These induced maps, of course, are not going to be injections. They're not, I mean, we don't know anything about these things. But what happens is that for each K, for each homology degree, and for each pairs of the parameters, I will have induced maps in homology. Now, if you look at this carefully, what you're seeing is what we call a representation of the Posets 0 to infinity. Okay, so here is we've been dealing with computational geometry. We've been dealing with simplicial complexes, homotopy and homology. Now let's look at some algebra. So what is a representation of a poset? A representation of a poset, let's do vector space. The representation of a vector spaces is a collection of vector spaces together with connecting homomorphisms whenever I have two comparable elements in the poset P. Okay. You can think of this as a functor as well. You change your poset into a category, saying that the objects of the category are the elements of P, and you will put a unique morphism between two elements whenever they're comparable, or actually the smaller one to the larger one, or the other way around, depending on your choice. So you can think of a representation as a functor from this category that you construct out of P into the category of vector spaces. All right. So this is essentially the definition of a representation. Essentially, what you're doing is you're trying to mimic the behavior of P, but using linear algebra. And this, in that sense, becomes that you see here there are two representations. The representation above is the representation of the poset 0 to infinity with its natural order in the category of simplicial complexes. And the second one is a representation in the category of vector spaces. Because when you take the homology, you destroy all of the structure and you just get the vector space out of a simplicial complex. Okay, so here you see two different representations. One is in the category of simplicial sets, and the second one is in the category of vector spaces. Now, here's a good thing. We know the full representation theory of the poset real numbers or 0 to infinity or any connected interval inside the real numbers. This poset is called tame, and every irreducible representation, we know what they are. They're of the following form. They're essentially a vector space, a constant vector space on an interval, a connected interval A to B. This interval could be an infinite interval as well. Although I wrote it as a closed interval, you can also take it as an infinite, half open, half closed, whatever. Okay. So we know the collection of irreducible representations, and they're very nice. They're just constant vector spaces over intervals. And you don't have to take this arbitrary vector space. You can decompose it into one-dimensional vector space. Essentially, this, I mean, V is one-dimensional because it has to be irreducible. Okay.
So do you mean here that every element, every object inside this interval is assigned V, and everything outside it assigned 0? Yeah,
exactly. Okay. So what happens is that you have this vector space living on the interval A to B, a one-dimensional vector space living on the interval AB.
Okay, thank you.
Remember what the representation was. For each real number, you have to have a vector space, and for each of these pairs, if the indices are comparable, you have to have a connecting morphism between them. But in the case of irreducibles, for each point, you have a one-dimensional vector space living on top. For another point, you have another vector space living on top. And for the irreducible representations, what you get really is just a one-dimensional vector space living on an interval A to B. In topological data, I'll explain that these have names. So now we know what the irreducible representations are. Okay. Irreducible representations of the poset are just one-dimensional vector spaces living on intervals, which means now I can take this homology of this filtered complex and I can split it into direct sum of irreducible representations. Okay, so I will get this factor in here. HK of my filtered simplicial complex splits into these pieces. Okay. So here's how you depict it. Let me explain how this picture works. So I have this Vietoris-Rips complex, and I change my epsilon. Now, here in this picture, you see this decomposition for H0 and H1. Of course, for H0, since individual points form classes in H0, the left-hand point of the interval are always going to be 0. in topological data lingo, AI is called the birth, and BI is called the death of a specific class. Remember, these things represent homology classes, and you can think of it as, and each v epsilon is one-dimensional. So all of these represent a single homology class. So AI is the birth time of this homology class, and BI is the death time of this homology class. Since individual points form classes in H0, the birth of every term in H0 happens at t equals 0. But of course, what will happen is that as you progress, as you increase epsilon, some of these classes are going to merge. But what we are going to say is that when they merge, one of them is going to die and the other one is going to continue on living. So these pink lines you see here essentially encode how these classes, well, you don't see it here, but what happens is that you see that some of these classes, short-lived ones, are going to merge with the other ones, and there's always going to be one single one remaining at the end because there is a single connected component if you choose epsilon to be very large. Situation is more complicated for H1. Why? Because as you increase epsilon, you see these points, and you kind of, we try to depict it here in this picture. What happens is that individual points stay separated, but once they start intersecting, or these balls start intersecting, you're going to form these triangles or polygons, and these polygons might have openings in between them. Remember, H1 encodes circle-like holes in your data set, essentially. So what happens is that some of these circle-like holes are going to start forming at certain specific epsilons, but since epsilon is still increasing, what happens is that at the end, they're all going to be filled. So in the H1 case, all of these classes will born at different times, but at the end, they will all die, as opposed to classes in H0. This whole theory, or this whole depiction, it depends on this very simple result in representation theory of Posets. Real line is tame, and irreducible representations are essentially these intervals or vector spaces living on these intervals.
I have a question about the previous slide. So here H0, I think, so as far as I understand it, epsilon 0, there I see 19 purple lines. I think they're supposed to correspond to the 19 distinct points.
Yeah.
In the first picture, but how do we choose 7 to be the one that lasts forever? Because it seems to be, is it
there is no reason for right. It's just we do it that way.
Okay, it's an arbitrary choice, right? You could have
chosen. It's an arbitrary choice. Actually, what you should be looking at, this picture tells you only, what essentially counts the dimension. So you shouldn't be looking at these things individually. This picture is misleading because what you're really interested in, how many classes, linearly independent classes, are there at a specific epsilon? That's the only thing I can measure.
Oh, I see. Okay, it's just as a visual aid, but otherwise I have to. Okay, look at that specific.
If you ask that question, I should get back into it. Let me show you this one. What happens is that, of course, these points will merge as you increase epsilon. So you read this diagram from low to high, okay? So here epsilon is 0, and here epsilon is large.
Can I ask you a question?
Sure. Sorry, before that, are we supposed to see that? Have you?
Sorry, let me correctly share my screen.
That was not visible.
Yeah. Sorry. Let me share the whole thing. Now, do you see it? Is this visible?
You see the...
No, I don't see. That should be something handwritten, right? I don't see anything.
Resume. Yeah. There you go.
Oh, yeah. Okay.
Now, look at this one. So what you're seeing here is a correct representation of pi 0 or h0 of x. Okay. At the beginning, you have these disjoint. So you have to read this from bottom to up this way. So here is epsilon equals 0, and here epsilon large. Okay. What happens is that at the beginning you have disjoint set of points, and then as you increase epsilon, these disks would start touching each other, and they would form individual connected components. So the full combinatorial information about how these classes merge is encoded in this picture. Okay, this is called dendrogram, and data analysis people have been using these things using what is called hierarchical clustering. I apologize about the handwriting, but since I've been typing so long, I forgot to write. Anyway, so there is something that we can learn. The topologists can learn something from data analysis people. They have the right representation of pi 0, especially for metric spaces, that how these, from sampler points, how the way these sampler points merge as you make these points fatter actually gives you a good information about the topology of this finite collection of points. Okay. Any question about the dendrogram? So
I want to ask, how do you decide these irreducible representations being intervals? Like small intervals will be submodule, wouldn't it? Or like you said, V should be reducible.
yeah,
I couldn't understand
V
all
is
this.
essentially one-dimensional because there
V
is
has
no.
to be
Yeah, V is
one-dimensional and irreducible. Like your work over vector spaces, is that?
Yeah, yeah. Of course, if it is not vector, I mean, it's not. We are not using a base field but a ring. The irreducible representation would be much more complicated.
And these intervals, how come the smaller ones are not sub representations?
Well, what happens
irreducible means
if the size increases as you increase epsilon, it splits because it's a vector space, right? So this on the interval, on any interval, the representation has to be constant, essentially, or the dimension has to be constant.
if I take a smaller interval, A to C, some C between A and B, that is smaller representation.
Oh,
is
no,
it
be
the
careful. Remember, there are also connecting maps. So you can't split the that way because it has to satisfy this compatibility condition. If I take these representations are essentially vector spaces or fibrations of vector spaces on the interval, and if 2 points are comparable, or in this case, A is less than B, you have to have a connecting morphism for the vector spaces on top. So they are not independent of each other.
Okay.
But, sorry, could I ask to extend on that point? So, so I'm assuming that these V epsilon, these irreducible ones have just identity maps for all numbers between A and B, or okay.
Yeah.
So how I'm sorry. So how would you realize like just like two-dimensional, the representation that's like 2 dimensions over R where the connecting maps are like rotation or something like that?
1 and 1, because in the case of, let's start with let's say you have this closed interval, and let's say assume that V is 2-dimensional. So at VA you have these 2-dimensional vector space. Take one of them and just follow that one. So that would, and since every vector space splits as a sum of, I mean, since every vector space has a basis, the irreducible representation would split as sum of 1-dimensional representation.
But sorry, but what if the connecting maps of the representation is like a rotation, like as you increase?
What happens is if you take this 1-dimensional object or this one basis element, it would have its trace on it. But just you normalize it to, remember these maps, even if they're not identity maps, all I'm interested in, you just change the representation into the constant one. This map is an element of GL1, so it's essentially a scalar object. You just normalize it to 1.
Okay.
It's isomorphic. Remember, at this point, I'm looking at isomorphism class. There's just an individual representation. For each of these irreducible representation, you're going to get just a collection of scalars from on the interval A to B. But as I said, I'm interested in the isomorphism classes at the moment, so I don't care. Because at this representation here, at the barcode representation, I'm counting dimensions anyway. So essentially, I'm looking at the Grothendieck group of irreducible representations of this poset. I'm not really interested in how these representations behave. At this moment, I'm interested in how they split. And since I'm looking at the split and the isomorphism classes, essentially I'm counting dimensions. Really, that's it. That's the only thing I do. If you want to look at the representation theory in more detail, of course, you have to look at these intricacies, but I'm not doing that at the moment. Are there any questions? Any other questions? Okay, so we can split the representations. In the case, of course, R, this R is what's called tame, so I know what these are, and barcodes. These things are called barcodes, by the way. So barcodes are enough because of the representation theory. But for Rn, the representation theory is wild. It's very, very difficult. It's not. You're not going to have anything nice like a barcode. And we need other tools. So this other tool that we came up with Ismail is a Matroid. So I'll give you the combinatorial definition. That doesn't make sense to me, but I'll give you another definition later. So here's the original definition. So let's start with the finite set. And from this finite set, I have an order ideal. What's an order ideal? It's what's called the down closed set. If I take an element in this order ideal, and if I take a subset of this element, and this subset has to also belong to the order ideal. Essentially, this is an abstract simplicial complex. Okay. And the order ideal is called a Matroid if I take two elements from the order ideal, such that one has less number of elements, then I can enlarge the smaller one using the elements in B in the order ideal. This is not a very intuitive definition, but the intuition behind it is that Matroids essentially model independence relations. The classical example of a Matroid is the dimension of the span of these elements. Okay. I don't like this definition. I don't use this definition. So let me give you a more, for me, it's more intuitive definition. So let's start with a Matroid. And let's define a function from the set of all subsets of E into the set of natural numbers by looking at these elements in the order ideal. These elements in the order ideal, essentially, you should think of them as independent sets. So essentially, you're counting the largest, the size of the largest independent set in X. So you extend this function to all subsets of E by looking at these largest independent subsets. So from a Matroid, we get a function. Now, and also this is a Poset function. That is, this R represents the order relation in the set of all subsets of E. Okay, if Y is a subset of X, then R of Y is less or equal than R of X. Now here's the theorem.
Sorry, about the definition, it seems to me that the output of the function is a set, not a natural number.
No, this is you see this one here means the number of elements of A.
Yeah, it's a set of
it's a type
numbers.
The sup. Sorry, I forgot to write.
Oh, okay.
Maximum. The maximum of all such elements. Okay, so I'm looking at the subsets of X which are independent. I'm counting the number of elements in that, and I'm taking the largest of those. So here's the theorem. It says, if I have an abstract map from the set of all subsets into N, a Poset map, then this comes from a matroid if and only if these two conditions are satisfied. One, R of X is dominated by the number of elements in X. So it can't be larger than the number of elements. And the second one, it satisfies the submodularity condition. This looks like inclusion-exclusion principle if this is equal, but I'm not going to take this to be equal, I'm taking it to be less or equal. Okay. It looks like a measure. Essentially, R looks like a measure, but it's not the full measure because in order just to be a measure, this has to be an equality here in the second condition. So this is like maybe a sub-measure, sub-modular. So what this result says is that matroids and rank functions are essentially equivalent. If I have a function like this, I have a matroid, and conversely, if I have a matroid, I have this rank function. Every rank function corresponds to a matroid, and every matroid corresponds to a rank function. So when I say rank function, I mean these two conditions are satisfied. Okay. From now on, if I say rank function, assume that all of these conditions are satisfied. So here comes our rank function from our filtered simplexes or filtered complexes. So let's start with the filtered complex. And the index set, you can assume any poset. I'm not making any assumption about the poset, but you can think of this 0 to infinity poset for our examples. I'm not looking at the simplicial complex, I'm looking at the singular complex. So from the simplicial complex, I write a differential graded object, and I'm looking at the kernel of the differential and also the image of the differential. For each P and for each K homology degree, I have these classes of cycles and I have the boundaries. Now I define a function by looking at the following equation. Give me a finite subset of homology classes, elements in the kernel. Take the span in the homology, add the boundaries, calculate the dimension, and then subtract the dimension of the boundaries. Essentially, what you're doing is you're looking at the dimension of the sub-vector space in the homology generated by these elements in A. Let me repeat. This is the dimension of subspace generated by A as homology inside the full homology group or full homology vector space. Now this, it's not very hard to show. This defines a rank function. And I will call this rank function cophenetic rank function or cophenetic matroid because it defines, I mean, this is the rank function, therefore it corresponds to a matroid.
What is you fix a K or take a?
Of course, yeah, this depends on K as well. I didn't write it here. So this R depends also on K.
And A is a subset of the
Space
chains
of
or
cycles.
Subset of CK then.
Yeah.
And
Or you can take it to be homology as well. Doesn't matter.
And you look
For
at
us, in the computational world, it's easier to work with the cycles because homology is defined up to an equivalence relation. So you must start with an equivalence class, and equivalence classes come from these cycles.
So this is from the vector space theory, I guess.
Yeah.
Would be the intersection or.
Yep.
So what?
First isomorphism theory.
Okay.
You're right. I mean, you have to look at the dimension of span of A minus the dimension of span of A intersection with the boundaries.
Okay. Okay. Thanks.
It's essentially first isomorphism. Yes, you're right. There are two different ways of writing the same thing. But this is easier. Why? Because intersection is difficult. You have to think in terms of computation. Why I prefer this one, not the other one. It's very difficult to calculate intersections, but it's very easy to calculate unions. Right? So this is for arbitrary subsets. Let's take two elements. So assume, I will start with a very specific example. Assume this was our running example essentially. Why? Our poset is the real numbers between 0 to infinity, and I have this filtered complex. I want to calculate something with that. Okay, take 2 cycles, calculate the run function on these 2 elements. Right, so I have an integer for each real number. Of course, for this belongs to a specific epsilon. So epsilon is for this x and y, epsilon is fixed. Or epsilon is fixed, and then I choose x and y. So every eta that comes after epsilon, I have an integer. Right? Now let's look at this number. I will follow this integer until the rank drops. And I will look at the infimum of all of these etas where the rank is strictly less than epsilon. So what does this calculate? In terms of H0, this means when these disks actually touch each other. Why? Because when these disks touch each other, I will put, or maybe I shouldn't say touch each other. There is another combinatorial condition. If I can find a path inside this complex that connect between these 2 points, I will have a one class whose image are these 2 points, which means they become linearly dependent, which means the rank will drop from 2 to 1. So this D corresponds when these classes merge. And since this is given by an infimum, it's not very difficult to show that this is a non-Archimedean metric. Non-Archimedean metric on what? Non-Archimedean metric not on points. For H0, it becomes a non-Archimedean point metric on points. But for higher K, this essentially gives you a metric on the homology classes, or not an ordinary metric, and a non-Archimedean metric on homology classes. Okay. So we call this Cophenetic distance. So what happens, since we have this thing, this is what we did with this slide so far, you can calculate, or you can draw these diagrams. Diagrams tell you, for H0 at least, tell you when these points are essentially touching each other, or when they form these connected components when epsilon increases. But now I have this same tool for higher homology classes. So I can essentially draw these dendrograms, or these connecting combinatorial information for higher homology classes. All right. Here is another thing you should notice. If you look at this diagram for points, what you're seeing is essentially cobordisms of points. For H0, remember what cobordism is. It's just a kind of like this theoretical tool that explains how certain manifolds actually look like each other. At this point, what you're looking at is a cobordism of points. So the hope is that if I do this for higher homology classes, since higher homology classes correspond to circle-like, sphere-like, or whatever SN-like holes in your data, so these diagrams, if I draw these dendrograms for higher homology classes, should be cobordisms of disjoint spheres in a higher dimensional setting.
So
for
from
that,
this
I need
sorry, Atabey. From this diagram, if I took 2 points, how do you decide the distance between 2 points? In the picture you had, like if I take 2 points.
Yeah, for this one, remember our points are sampled from a metric space. So I have a way of thickening points. Take a point, instead of using the point, put a disk of radius epsilon on that point and then increase epsilon. So these points eventually start, or these disks will eventually start touching each other. When they touch, I will form, and remember the combinatorial information on the simplicial complex is given by how these disks touch each other. So 2 points, if you're looking at this diagram here, 2 points merge at the very beginning when their disks touch each other. for the other ones, the situation is a little more complicated.
I mean, if you did something similar for higher homology, HK or something,
Yeah.
You will have a similar idea that the metric means something like when the balls make that two homology classes equivalent.
Yeah, but the situation is a little more complicated. Let me show you an example. Let's say I have this thing. Let's say I have the annulus, right? Let's assume for the moment that at some epsilon I detected the inner circle, and later on I detected the outer circle. But the in-between is not filled yet. Remember, as epsilon increases, I'm filling my complex areas, all right? So let's say this is epsilon 0, and let's say this is detected at epsilon 1. Let's also assume that this is completely filled at epsilon 2. So at epsilon 0, I have a single class. At epsilon 1, later on, I will get a second class appearing. But at epsilon 2, these two will merge. So this is epsilon 0. This is epsilon 1, and then epsilon 2. Does this make sense?
So what is the distance between two classes then? Is it which one?
In this case, when the distance would be epsilon 2 minus epsilon 1.
Epsilon 2 minus epsilon.
Well, actually, I have to be careful because these two classes don't live in the same place, right? It lives in filtration degree epsilon 0. It has an image, or it has a class which lies in epsilon 0 here. I can calculate the distance between these two, and so this is epsilon 1, and that distance has to be when they are born, and this is when they merge, so the distance is going to be epsilon 2 minus epsilon 1.
Thanks.
Does it make sense?
Yeah. Thanks.
Yeah. Now for this, I need one last concept. This is called minimally reducible set. And this concept comes from Matroids. So take any Matroid, that is, take any rank function. I will call a subset minimally reducible if its rank is not maximal, but one less. Okay. So the maximal rank you can have, remember, has to be is bounded by the number of elements in the set. So if I have these two things are equal, then this set is called an independent set. So I don't want an independent set, but I need something that is maximal in that sense. Why this is minimal is I call this minimal is it's a technical thing. But not only that, if I take any subset of A, not equal to A, it has maximal rank. So the set doesn't have maximal rank, but all of its subsets have maximal rank. You can think of it as vectors in which there is only one linear dependence relation. Okay. This is what we are trying to do. Take K cycles. I have a rank function, so I have a Matroid. Take a minimally reducible set. That minimally reducible set corresponds to a K-sphere with a certain number of punctures. Or you can think of it as a cobordism of disjoint union of spheres. Okay. So what happens is that I don't have, for H0, this is my cobordism. This is for H0. For higher K, I have a similar picture, but these things here correspond to spheres, and these merging information correspond to spheres with punctures. So I have these spheres with punctures merging as epsilon increases. Okay. There are lots of different ways you can actually write this information. You can write it as an operad, you can write it as a cobordism, you can write it as matroid, as I did over here. There are many different representations, but the main idea is that they all boil down to these minimally reducible sets in this matroid that I'm trying to write. Okay. So that's all I have. Thank you very much for listening.
Okay, thank you. Thank you very much. Okay, are there any questions from the audience?
In the very beginning, you said M should be equal to the union of open balls.
Yeah.
So you're always considering open subsets of the Euclidean space?
Not necessarily, but since the Borsuk-Ulam's theorem work with open covers, start with any open cover, or relatively, I mean, you can take these closed sets, but they have to have an non-empty interior, and the unions of these non-empty interiors should give M. You can work with closed sets as long as their interiors satisfy the condition in the nerve theorem, or any collection of sets as long as their interior non-empty union is the whole thing.
So that means you're taking a thickening of the topological space you started with, or?
You can think of it that way as well, but no, I'm not doing anything here or anything. The only thing I need is the combinatorial information of these set, the covering. Other than that, I'm not using anything.
Okay.
Because from this collection of sets, I'm writing a simplicial complex, looking at a specific combinatorial condition.
Okay, thank you.
But you can think, or you can, I mean, you're right. You can think of it as a thickening of the original manifold, or the subset, or the embedded manifold thickened in Rn. If it has if it has a smaller dimension, the embedded manifold might have boundary, and it may have the same dimension as Rn. So I'm also including that case as well. The manifolds here I put no condition. It could be with boundaries. It could be with, you can even work with orbifolds. I mean, things with non-smooth points, whatever. Because as long as you get this, you can concoct this combinatorial gadget. The rest is just the same for, I mean, the whole computation is the same.
So Atabey, what does the theorem say exactly? I'm not sure I understand. Comes from X and the sphere is in the data space?
Yeah, here's the thing. Remember, what I'm trying to do, essentially, I have this distance function, right? I have this distance function, a non-Archimedean distance function on homology classes, okay? And I want to represent, I mean, this distance function gives me good information, but I need something visual. I want to represent these classes, or the relationship between classes, or the information coming from this non-Archimedean matrix in a visual form. In the case of H0, I have this diagram, this dendrogram. And in the case of H0, this distance is essentially similar, not very different. It's not the same thing, but it's similar, or kind of the information is similar to the original matrix. But as you go in higher classes, this distance has no intuitive meaning whatsoever at the point. It just tells you how these classes merge, when they merge, etc. But I want to represent this in a visual form. So how do I do that? My idea was that this picture here is a zero or one-dimensional cobordisms of zero-dimensional manifold. Essentially just how points merge, right? So I want to be able to do the same thing for higher homology classes. What do higher homology classes represent? Spheres. Or if you use Hurewicz theorem, provided that you have this connectivity information, whatever. So philosophically, the homology classes come from embedded spheres in your data set. So the hope is that I want to be able to write this merging information as cobordisms of these disjoint spheres. And what's the best way of writing it is going to be just, if I want to write these k-dimensional spheres as cobordism, I need a k+1 dimensional sphere with certain number of holes in them, right? Because that corresponds to a cobordism of k-dimensional spheres. So this is the theorem. If I want to do that, I shouldn't be looking at arbitrary subsets of these classes. These classes have to satisfy certain combinatorial information, and that combinatorial information is given by this definition of minimal irreducible sets. Why? Now look at this one. It says every subset is linearly independent except the largest set itself. So what does this mean? I have one large circle and smaller circles in between them inside, and the in-between is filled. That's essentially what it is, which means I have a k+1 dimensional spheres with certain number of holes in them. That's essentially, I converted this combinatorial information into a topological information as a picture of a cobordism. Does this answer your question?
Yes, it's much. I still don't understand what minimal irreducible, so
yeah, minimal irreducible. Let me show you the picture.
Why is it important?
Picture worth a lot of words. So here is a minimal irreducible set in dimension 2 or dimension 1, in dimension 1 homology. So here is my class H0, A0, A1, A2, and A3, okay? A0 is a homology class, A1 is a homology class, A2 and A3 is a homology class. Here's the minimal irreducible set. A0, A1, A2, and A3. Why? If I take these things by themselves, if I take these two, or if I take these three, the rank of these things is 3. They span a 2-dimensional space set or a 3-dimensional set. If I take any subset of this, they are linearly independent. Except when I take all of them together, they are not linearly independent. The rank drops by 1 because of this, because of the fact that this is filled inside. But what is this? This is a 2-sphere with 4 punctures. All right. So this is the intuition behind the theorem.
Okay.
And what happens is that as epsilon increases, you start seeing merging of this set with something else. So here is another set. And as epsilon increases, these things would merge. So what happens is that you take these spheres and you start merging them. All right. So when I had the dendrogram for H0, and now I have these spheres with punctures and merging of these spheres with punctures for higher K.
There is also this shift operators and then this algebra picture. Does this go together well with that, or
that I don't know?
Okay.
Because
that
depends on promoting let's say a K class to a K+1 class by using the suspension. Right.
There's a homological algebra of these things.
Correct.
as
Yeah, in a sense, what you're saying is that these things, instead of thinking them as vector spaces over the base field, you can think of them as modules over the polynomial algebra, where this generator comes from the suspension by S1, right? Smash product with S1. So yeah, that you can also do it that way. But that requires a different argument. Why? Now, I'm trying to think of them as vector spaces, so basis elements. I write these basis elements. In the case of Kx, that is suspension, I have to think of them as modules over the polynomial ring Kx. And the representation theory of that is much more complicated. I don't have basis anymore. So it's a Kx is somebody wrote something. Yeah. Kx has homological dimension 1, so the projectives are a little different than frees, the free modules. So actually, every projective is free in Kx. Sorry, but the representation is a little more complicated than just the vector spaces. But you're right.
Like, is there a connection to your picture with the
I don't know. We haven't thought about this. As I said, this is an ongoing project.
Okay, that will be interesting.
Yeah, the suspension thing is interesting, but at the moment we need to do some calculations. So for the simplest calculation, even the basis elements counting or looking at these rungs are difficult. Here's a computational fact. Calculating the rank of a matrix is an expensive operation, especially if you have, here's the discussion that I wanted to give at the beginning. Topological data analysis is a good study in theory. In practice, it is extremely complicated. Why? Because the computational complexity is huge. Have you ever tried to calculate the homology of a simplicial complex, let's say 60,000 elements? Don't even do it because it's exponential. It's very, very difficult. So you have to find these shortcuts, and they're not easy to come by. It's very difficult. Calculating rank of a matrix is a cubic operation. If you have an n by n matrix, if you want to calculate its rank, it's expensive. It's not an easy thing to do. And this rank function, which is the whole machinery behind this whole this presentation, it depends on the rank function, and it's an expensive gadget to calculate. Homology is even worse. So it's an exponential gadget. There isn't much hope. So for me, TDA is a good thing to study in theory, but when you start making calculations, it's a different thing.
I asked this to Barish too, but do you have like programs which is open source that you can play with?
Smile is writing, my PhD students is writing something. So, but there are topological data libraries, very fast, very efficient.
Where is that library? Is there a just searchable thing, topological data library?
Yeah, all right. It's a couple of them here. They all use Python. Sorry. Guti is a good one. This is Python based. Here's a Java based one. But if you search for topological data analysis computational libraries, you'll find many. There is one, I forgot the name, a new one coming from a research group in France, which is supposed to be the new one. A lot of people are using it at the moment, but I forgot. Style knows these things better than I do. I do theory, he does computations. So.
I think Barish mentioned that French one.
Yeah. Yeah.
You should talk to him. He's seems like deep into it now.
As I said, there is money in there, and a lot of students. I have 4 PhD students. 2 of them are doing this thing, and 2 of them are doing theory. So, yeah, it's as I said, there are more jobs. There is more money, and if you can't find a job in academia in TDA, you can find a job in the industry. So, at this point, I'm telling all of my students, it's a crime. It is actually an unconscionable thing to study theory in math at the moment because the job market is terrible. So Yeah, you're right. TDA is in fashion at the moment.
We shouldn't be so pessimistic. I think let's see. Another thing Barish said yesterday, which we can, I guess, ask to Matthew, that these barcodes and so on, you cannot put into machine learning. Like the barcodes, you cannot transfer it to this where you need them. What does this mean? I don't know what it means really.
Yeah,
like barcodes.
This H0 part essentially is known. Machine learning people call it hierarchical clustering. This was the thing that I was showing you here. This is known. For higher ones, we don't know. I mean, this is what I'm trying to do essentially. For higher homology, we need representations like that. And this cobordism business actually might capture that. So Barish was talking about they don't have a representation. Well, I mean, we are going to propose that we have a representation, but up until this point, there was not. But I mean, computationally expensive, really bad. Even like a reasonable thing like 200 points, 100 points, simplicial complex, it will take 4 to 5 hours on a CPU with 80 cores. It is really expensive to calculate homology.
Matthew, does any of these comes in your where you're doing?
Nope. But
you know, Matthew moved into industry, right, Atabey?
No, I didn't know.
Yeah. I'm following the advice you're giving your students. But it's much lower tech than everything that you were talking about, both in terms of theory and even the applications are pretty low tech. Okay. Thanks for the talk.
Okay, yeah, maybe it's time to conclude. So yeah, thank you very much for the talk on behalf of the audience.
Yep.
Maybe we can have more discussions right after.